In the days when I used to teach spectroscopy, I had a very straightforward systematic method. I called it my ABC system of spectroscopy in general, because it could be paralleled from rotational to vibration to electronic. So A was a classical description of the system. B was the quantum mechanical description. Then C, you solve the Schrödinger equation. Then D, selection rules. E, transition frequency. F, you get the spectrum. And G, analysis. And then H, experimental. And I, advanced details. And J, information that you can get from it. So if you take rotational spectroscopy, you have a rotating rigid molecule as a starter. Then you have the quantum mechanical description, where the energy goes as Bj squared or Bj j plus 1 when you analyze it and solve the equation. The selection rules for a simple case of delta J plus or minus 1 for a linear molecule. And the energies, when you get to the transition frequencies, delta E goes as 2B into J plus 1. Then there's a Boltzmann factor involved. You get the spectrum, and I showed here, of carbon monoxide. Determine the B value, which gives you the rotational, the bond length from the rotational frequencies. The infrared spectrum is experimental or microwave spectrum. Advanced details, a centrifugal distortion, the molecule expands a little as it rotates. You have to take that into account. Maybe Raman spectroscopy must be required. And you get accurate structures to 1 part in, say, 1,000. Maybe 1 part in 10,000. But you have to decide what that actually means. On vibrations, you have a spring sort of a picture of two balls oscillating. Then you take the harmonic oscillator for a quantum system, and you get the energy going as V plus a half. In the simplest case, for non-degenerate systems, you get the sort of very simple harmonic potential, and you get these beautiful waves. From that you can determine the vibrational frequency. You get an infrared spectrum, the fingerprint, in this case HCN. From that you can determine what sort of molecule you've got, if it's not too difficult. And then use infrared spectrometers. Real molecules, of course, are anharmonic, and you've got to take that into account. Raman spectroscopy can be used again, and you can use lasers for laser spectroscopy. Electronic spectrum is more complicated, really. Here you have an electron or electrons which are holding the molecule together, and as a photon comes in, you excite the electron to various levels, and usually that's estimated from molecular orbital theory. Very simple cases for diatomic molecules, you get relatively straightforward molecular orbital. You can take energy as it jumps from one orbital to another one. In the case of an atom, you get the Balmer series for a very simple Balmer series pattern, which you can analyze. In the case of a molecule, you can sometimes get the vibrational frequency in the lower state to the excited state. You get in some cases you can determine the rotational structure and get the bond length in the upper and lower states. Sometimes it's pre-dissociated, but by and large you use UV grating spectrometers or lasers to detect these particular spectra. And I've got this all on one sheet. So basically the whole of molecular spectroscopy on one sheet of paper.